Welcome to the guided practice 7. These are our 6.2 problems. And this is on volumes of revolution. So keep in mind, we are taking an area and we are revolving around it, a specific line, either the axis or a line that's specified, and then asking to find the volume. And if you remember that the way that this is done, it's done by two different methods. So disks, we take the volume as pi times the integral from a to b of the radius squared dx, okay, or dy. And then if we're working with a washer, meaning it's not solid, there's kind of a space in the middle, our volume is the integral from pi times the integral from a to b of what we're going to call our outside radius, our r0 squared, minus our inside radius, our ri squared, dx. Now, of course, we can switch from dx to dy. And so that's what we're going to do here. So to start for these guided practice problems, we're going to start by sketching always, okay? So if I sketch this graph, x squared looks like this, and 2x, and to be honest, I'm actually going to get their intersection first so I know where I'm going. So let's set 2x equal to x squared, and that's x squared minus 2x equals 0. Factor out your x. That gives us x equals 0 and x equals 2. So they're going to intersect here and somewhere out here at 2. And the line y equals 2x, it has a y-intercept of 0, and you're going up to right 1. So it looks something like that. Okay, and so what we're doing is we're revolving this area around the x-axis. Okay, so when I revolve it, I get a mirror image over here. Actually, yeah. I get a mirror image over here, and then it's spun around to create a three-dimensional image, okay? Now, this is a washer, right? Because the outside is this line, and then the inside is the curve. So when I think about zooming in here and finding my radius, the outside radius is going to go from your x-axis all the way to your outside line. So that's my outside, or my RO, and my radius for the inside goes to the inside of the washer. So that's my RI. So when I set up the volume, my volume is going to be pi times the integral, and you can see we're going from x equals 0 to x equals 2. Again, that's from finding the points where they intersect. So from this information right here. And then we want the outer radius squared, okay? And that's because we're finding the volume of if we just had that big disk, right? If we found the volume for the outer curve, that would give us a solid kind of cone-looking thing here. And then we're going to take away the volume of the inside piece so that we have just left that washer. So we want the outside radius squared. My outside radius is the line, so that's 2x. And I'm going to square it. And then I want my inside radius, which is the x squared, and I'm going to square that. And because these are all in terms of x's, I integrate with respect to x. So I have pi, integral from 0 to 2, and now I'm going to simplify here. So this is 4x squared minus x to the 4th dx. And then we're just evaluating our integral. So 4/3 x cubed minus 1/5 x to the 5th. Evaluated from 0 to 2. When we plug in 2, we get pi times 2 cubed is 8 times 4 is 32 over 3 minus 32 over 5. And when you plug in 0, you get 0, so I'm not even going to write it. They both have a 32 in it, so I'm going to move that outside with the pi, and then I'm just taking 1/3 minus 1/5, which turns out, I'm doing this without a calculator, so this turns out to be 5 minus 3 is 2 over 15. So that means I get 64 pi over 15 as my volume. Okay, and number 2, the main difference here is that we're going to rotate this around the y-axis. And anytime you're rotating it along something vertical, you're going to switch your variable in integration to y. So in this particular case, I'm going to think about this both in terms of, so I'll sketch it first, and then we know that we're going to be switching the second one in terms of x's, as x equals, just like we did with area. So if I've got the plane that I'm working with here, 1 plus y squared is a parabola on its side with intercept 1, and it opens up, or in this case, to the right towards the positives, because the y squared is positive. So there's my curve there. And then we want the line y equals x minus 3. So that's the line with intercept -3 and with slope 1. So it's going to kind of cut things just like this. And we're revolving this area around the y-axis. So if I mirror image this, see if I can create the three-dimensional shape. It looks something like this, spun around there. Okay. And again, the key thing that you want here is you want to know what your 2 radii are. So again, this is a washer because I have space in the middle that's taken out. And I want the distance from my axis, from where I spun it, the y-axis, to my outside of the shape. Okay, and so that's the line. That's my R0, my R outside. And then I want the distance from that axis to the curve, to the inside part, which is my Ri. Okay, so next what we need to do is we need to find our boundaries. So we need to know what is this point and this point so that we know our bounds of integration. So we're going to set our equations equal to one another. So first thing I'm going to do is solve the second one for x. So I'm going to add 3 to both sides, and that's going to give us that x is equal to y plus 3. Okay, that gives us both our curve in terms of y's, so that they match, and it's going to allow me to set them equal. So now I set my x's equal, so I have y plus 3 is 1 plus y squared. Okay, I'm going to subtract a y and a 3 to the other side so that I can get it equal to 0. So I have y squared minus y and minus 2. And that factors nicely for us. So that's y minus 2, y plus 1. So I get y equals 2 and y equals -1. So that means this lower value here is my -1, and my upper value here is y equals not 3, but 2. And that tells me that when I go to set up my integral, the volume is going to be pi times the integral from -1 to 2. And I want the outer one squared, okay? So that means I'm taking the line, which is the y plus 3, and squaring that. And subtracting it from that, we're taking the inside radius squared, and that is the curve, the 1 plus y squared, squared, dy, because everything's in terms of y. Then you're going to go ahead and simplify this. So this is y squared plus 6y plus 9 minus, squaring the second one, that's 1 plus 2y squared plus y to the 4th dy. Now don't forget to distribute your negative there. So this is pi, integral from -1 to 2. And I'm going to distribute the negative. That's going to give me a -y to the 4th minus y squared plus 6y plus 8 if I'm combining my like terms. Now I'm ready to evaluate my integral, so I've got the pi out front. I'm going to leave it there and take my antiderivative. So -1/5 y to the 5th minus 1/3 y cubed plus 3y squared plus 8y evaluated from -1 to 2. Okay, and here we've got a lot going on, so let's plug it all in. We've got pi times all of this. So 2 to the 5th is 32, so this is -32 over 5. Sorry, guys. Minus 8 over 3. Plus 12 plus 16. Minus, when you plug in -1. So -1 to the 5th is -1 times -1 is positive 1/5. Plus 1/3 when you plug in the -1 to the y cubed. Plus 3 minus 8. And let's see, when we do all of that, and I'm going to go plug that in somewhere else. Let's see, where's my Wolfram Alpha? Nope, not what we're looking for. Thought I had this up. All right, we've got negative 32 over 5. Is it plus or minus? Minus 8/3. Plus 28, I think it is. 16 and 12 is 28. Then we are subtracting 1/5 and 1/3 and adding 5. So minus 1/5 minus 1/3 and adding 5. And that gives us 117 over 5, as you can see there on the screen. So this is pi times 117, and I'll switch that. 117 pi over 15, and that's our answer for the volume. Okay. So again, key thing to remember about when you're switching to the y-axis is that anytime you're revolving around a vertical axis, you're going to end up integrating with respect to y. Just like when we did areas, when one of your equations is written as x equals, you're going to write them all as x equals and turn it into integration with respect to y. I'm going to do the other two problems in a separate video for you.